Right now, as you read this, a sequence of solar eruptions launched from the surface of the Sun between July 24th and July 28th, 2026 is moving through the inner solar system toward Earth. NOAA's Space Weather Prediction Center has issued geomagnetic storm watches covering July 29th through July 31. The first wave of that sequence has already arrived, delivering G1 to G2 conditions, minor to moderate geomagnetic storm levels. But the more dangerous follow-on wave, driven by a phenomenon that space weather forecasters call a cannibal CME, is still in transit. And the honest assessment from NOAA and the professional space weather forecasting community is this. Nobody knows exactly how hard this one is going to hit until it is almost on top of us. That uncertainty is not a failure of science. It is the defining characteristic of the single most unpredictable and potentially most damaging space weather threat that Earth faces. And understanding what is building right now and why this summer of 2026 has become one of the most active space weather periods in years requires understanding what solar storms actually do to the infrastructure that modern civilization depends on. The Sun is a star undergoing a continuous cycle of magnetic activity that spans approximately 11 years from one minimum of activity to the next. Solar Cycle 25 began in December 2019. NOAA and NASA announced on October 15, 2024, that the Sun had reached solar maximum, the peak of activity in this cycle, with the smoothed sunspot number peak falling around October 11th to 12th, 2024. The period following a solar maximum does not immediately become quiet. The decline is gradual and uneven, with sunspot counts remaining significantly elevated compared to the quiet years at the bottom of the previous cycle. Space weather. Researchers have characterized the period extending from early 2026 through mid-2027 as a window of sustained elevated risk for satellite infrastructure and high-latitude power grids. That elevated risk window is what we are currently inside. The solar maximum has passed, but the Sun's magnetic field has not yet settled back toward the relatively calm configuration of solar minimum. Multiple active regions, sunspot groups with complex, twisted magnetic configurations capable of producing X-class flares, continue to rotate across the Earth-facing solar disk. And during July 2026, several of them have been particularly productive. Like and subscribe, because what happened on July 4th, 2026, and what is building again right now for July 29th through 31, illustrates exactly why space weather forecasting is both critically important and genuinely difficult. The active period that built through late June and early July 2020 Essex produced a series of significant events. An X1.1 solar flare from active region 4479 on June 30th, 2026 launched a full halo coronal mass ejection, a plasma cloud expanding in all directions from the eruption site, confirmed by coronagraph imagery from the ESA NASA SOHO satellite. NOAA's Space Weather Prediction Center issued a G2, moderate geomagnetic storm watch with potential impacts including power grid fluctuations and voltage alarms in high-latitude systems, satellite orientation irregularities, increased drag on low Earth orbit satellites, fading of high-frequency radio propagation at high latitudes, and aurora visibility as far south as New York, Wisconsin, and Washington State. That event was followed by a 4th of July surprise, a G3, storm that arrived 2 full levels stronger than NOAA had predicted in the hours before impact. On July 4th, 2026, a G3 event arrived 2 full levels stronger than predicted. That kind of forecast error, not in the direction of the storm or the timing, but in the intensity, is characteristic of the specific meteorological challenge that makes space weather the most difficult short-range natural hazard prediction problem in science. To understand why, you have to understand what determines how damaging a coronal mass ejection actually is when it reaches Earth. A CME is a cloud of magnetized plasma ejected from the Sun's corona at speeds typically ranging from a few hundred to over 2,000 kilometers per second. The cloud carries a magnetic field embedded within it. When that cloud reaches Earth and interacts with the magnetosphere, the magnetic field that protects the planet, the critical variable is the orientation of the CME's embedded magnetic field relative to Earth's own. If the CME's magnetic field is oriented northward, it largely slides past Earth's magnetosphere with minimal interaction, and the resulting geomagnetic disturbance is modest. If the CME's magnetic field is oriented southward, on what scientists call a negative busy, it connects directly to Earth's magnetic field in a process called magnetic reconnection, driving charged particles deep into the magnetosphere and generating the intense geomagnetic currents that produce severe space weather effects. The southward Beasy orientation is the key variable that determines whether a storm reaches G1, G3, or G5, and that variable cannot be measured with confidence until the CME's leading edge passes the L1 Lagrange point, a monitoring position approximately 1.5 million kilometers from Earth, which provides roughly 15 to 60 minutes of warning before impact. For a storm moving at 1,000 kilometers per second or faster, that is the complete advance warning. Window available to infrastructure operators who need to take protective action. Like and subscribe, because the Cannibal CME that is building for late July 2026 carries additional uncertainty beyond the standard BZIT problem, and understanding it requires understanding what happens when CMEs collide. What makes this follow-on wave structurally more complex than the initial event is a phenomenon called CME interaction, what forecasters and physicists sometimes refer to as Cannibal CME formation. When multiple CMEs launch from the Sun in rapid succession, a faster moving ejection can overtake and merge with a slower one still in transit through the inner solar system. That interaction, known as a Cannibal CME event, produces what physicists call complex ejecta, a merged structure with amplified magnetic energy and less predictable internal field orientation. The merging process shears and tangles the magnetic fields of both eruptions, producing a combined structure whose internal BZ orientation is genuinely harder to model than either ejection would be individually. The merged structure's internal magnetic field orientation is less stable and harder to model, meaning the B's component's behavior becomes harder to predict in advance. The history of Cannibal CME events illustrates both the danger and the unpredictability of this specific phenomenon. The May 2024 Cannibal CME storm reached G5, the strongest in 2 decades, a G5 event that pushed aurora as far as Mexico and stressed power grid operators worldwide. A June 2026 Cannibal CME reached G3 and pushed aurora to northern France and New Zealand. Most cannibal. CMEs, including a well-documented July 2023 case, produce only G1 to G2 minor to moderate effects. Same mechanism, wildly different outcomes. The factor separating a G5 catastrophe from a G1 inconvenience is the internal magnetic field structure of the merged ejection, a variable that cannot be measured or predicted before the material reaches the L1 monitoring point. The honest forecast for late July 2026 is not storm or no storm. It is probably minor, possibly nothing, and we won't know which until the material is nearly on top of us. That uncertainty is why what happened in January 2026 remains the benchmark event that space weather professionals are using as a reference point for the current active period. On January 18, 2026, the Sun erupted with a powerful X-class flare that hurled a fast-moving coronal mass ejection directly toward Earth. The CME was estimated to travel at approximately 400 kilometers per second, but its actual arrival speed was closer to 1,600 kilometers per second. The resulting geomagnetic storm reached G4, severe levels, with impact arriving at 2:38 p.m. Eastern Time on January 19th. The solar radiation storm that accompanied the January event reached S4, severe, levels on the radiation scale, placing it at the top of the list of most intense radiation storms in the GOES satellite records. The resulting geomagnetic storm reached the top of the warning scales and had the potential to affect astronauts in space and may impact Earth-orbiting satellites, power grids, and aviation. That event, occurring in the same elevated risk window that 2026 represents on the declining slope of solar cycle 25, is a reminder that the period after solar maximum is not a period of immediate safety. Like and subscribe, because the practical infrastructure impacts of a severe geomagnetic storm are things that most people have never thought through, and understanding them changes how you think about space weather entirely. At G3 to G4 storm levels, power grid operators at high latitudes, in Canada, Scandinavia, Northern Europe, and the northern United States, face the most immediate and serious risk from what are called geomagnetically induced currents. When a geomagnetic storm drives electrical currents through the Earth's crust, those currents find their way into long metallic structures, power transmission lines, pipelines, and railway tracks that serve as conductors. In power grids, these induced currents can saturate the iron cores of large power transformers, causing them to overheat and potentially fail. The large, high-voltage transformers that are critical to grid function are extraordinarily expensive, often custom-built, weighing hundreds of tons and carrying lead times of 12 to 18 months for replacement. A cascading failure of transformers across a regional grid could produce extended blackouts lasting not days but weeks or months, and the supply chain for replacement equipment is not configured to respond rapidly to mass failures across multiple countries simultaneously. Satellite operators face a different set of risks. At G3 and above, the upper atmosphere expands as solar energy heats it, increasing the drag on satellites in low Earth orbit. That increased drag can alter orbital paths, reduce satellite lifetimes, and in the most severe cases, cause rapid, uncontrolled re-entry. The GPS satellite network, which operates at much higher altitude, is affected differently not by orbital drag, but by ionospheric disturbances that introduce errors into GPS timing signals, potentially reducing positioning accuracy to meters rather than centimeters for critical applications, including precision aviation, navigation, and autonomous vehicle systems, high-frequency radio communications, which aviation and maritime operations rely on for transpolar routes in remote areas, can experience complete blackout during severe geomagnetic storm conditions. All of these effects cascade together during a significant event, hitting multiple sectors simultaneously. The January 2026 G4 event provided a real-world test of the monitoring and warning systems that have been built to protect infrastructure from exactly these consequences. The accurate arrival forecast for a subsequent June 2026 event, correct to within hours, reflects ongoing improvements in CME propagation modeling. NOAA's June 6th watch predicted CME impact by midday UTC on June 8th. The shock arrived as forecast. For every additional hour of advance warning a grid operator receives, protective switching maneuvers become easier and transformer damage becomes less likely. Those improvements in the accuracy and timeliness of space weather forecasting represent one of the most consequential areas of investment in modern infrastructure protection. A 30-minute warning before a G4 or G5 impact gives grid operators enough time to reduce load, trip vulnerable transformer circuits, and bring backup generation online before the induced currents arrive. Without that warning, the damage potential is dramatically higher. Like and subscribe. Because the Carrington event of 1859 is the benchmark that space weather researchers keep returning to when they calculate what the worst-case scenario actually looks like. The Carrington event was a solar storm of extraordinary magnitude, estimated at G5, or above, likely the strongest geomagnetic storm in the past several centuries of reliable human observation. A CME creates gusts and shock waves in the solar wind, which, if heading towards Earth, can take anything from 18 hours to a few days to reach us. When a CME arrives at Earth, it stresses its magnetic field, causing a geomagnetic storm. This makes compass needles wander and can provoke damaging surges of electrical current in long metallic structures, such as power lines and pipelines. In 1859, the only long metallic structures connecting significant portions of the population were telegraph lines. Those lines caught fire. Telegraph operators received electrical shocks from their equipment. The aurora was visible in tropical regions. The entire event lasted several days. A Carrington-class event today, arriving on a planet whose critical infrastructure is built on electromagnetic systems, satellite navigation, internet-connected control systems, and power grids that span entire continents, would produce consequences that experts have modeled in terms of trillions of dollars in damage and multi-year recovery timelines. The current space weather situation in late July 2026 is not a Carrington event. The forecast for the July 29th to 31 window suggests G2 to G3 conditions as the most probable outcome. Significant, disruptive, but far below the catastrophic threshold, but the same monitoring infrastructure that is tracking the cannibal CME sequence heading toward Earth this week is the infrastructure that would provide the warning if something more severe were to follow in the remaining months of the solar cycle 25 decline. The Sun is not done. The solar disk currently hosts multiple sunspot regions with significant magnetic complexity, and filament eruptions continue to hurl plasma into space from the same active areas that produced this week's events. The elevated risk window identified by space weather researchers runs through mid-2027. What has happened in January 2026, in June 2026, and in late July 2026 is the pattern of that elevated risk expressing itself. Whether something more severe will arrive before solar cycle 25 reaches its quiet minimum is a question that no model can answer in advance, and that the monitoring systems watching the sun right now are designed to provide the earliest possible warning for when it does. The specific concern about the July 29th to 31 window goes beyond the cannibal CME structure alone. The timing places this event during a period when multiple active regions are still producing eruptions, meaning any storm that arrives could be followed by additional CMEs before the magnetosphere has fully recovered. Back-to-back storms produce significantly worse effects on power grids than an equivalent single storm, because protective measures implemented during the first impact may not be restored before the second arrives. The late July sequence involves multiple CMEs from multiple launch events, with at least one cannibal merger in progress, and additional faint eruptions, potentially delivering glancing blows in the following days. The practical advice that space weather agencies issue during elevated risk periods is straightforward and does not require specialized technical knowledge to follow. Satellite operators should consider moving sensitive spacecraft into safe modes during the peak storm window, reducing their exposure to energetic particle bombardment. Aviation operators routing transpolar flights should evaluate alternate routes that avoid the high-latitude ionospheric disruptions that HF radio blackouts create. Power grid operators in high-latitude regions have playbooks for this scenario: load reduction, switching of vulnerable transformer circuits, increased monitoring of geomagnetically induced current levels on transmission lines. The public guidance is simpler. Be aware that GPS accuracy may degrade temporarily, that high-frequency radio may be disrupted, that power fluctuations are possible in northern regions, and that aurora may be visible at unusually low latitudes if the storm intensifies to G2 or G3 levels. Like and subscribe. Because the question of whether humanity is adequately prepared for a major solar storm is one that serious scientific and government institutions have been studying for years, with conclusions that are simultaneously reassuring and sobering. The United States government's National Space Weather Action Plan, updated most recently in 2024, represents the most comprehensive governmental framework for addressing the solar storm threat across multiple agencies simultaneously. It covers forecasting improvements, infrastructure, protection standards, international coordination with space weather agencies in Europe, Japan, and Australia, and the development of backup communication systems for scenarios where GPS and HF radio are both disrupted. The European Union has developed similar frameworks through ESA's Space Weather Coordination Center. Japan's National Institute of Information and Decommunications Technology operates a dedicated space weather forecasting center that is among the most advanced in the world. International coordination on space weather has improved substantially in the past decade, driven partly by the May 2024 G5 event that served as the largest real-world test of monitoring and response systems since the Halloween storms of 2003. What those systems revealed in May 2024 and what the January 2026 G4 event reinforced is that the warning infrastructure works significantly better than a decade ago, and that the most vulnerable points are not in the forecasting capability, but in translating those forecasts into protective action by infrastructure operators. A grid operator with an accurate warning and a clear playbook will protect their infrastructure. One who lacks the playbook or the authority to act quickly will not. The gap between those two scenarios is where the investment in space weather preparedness is most urgently needed. What is happening in late July 2026, tracked in real time by monitoring satellites at L1, by ground-based magnetometer networks, and by the 24-hour centers at NOAA's Space Weather Prediction Center, validates exactly why that window from 2026 through mid-2027 has been flagged with concern since the solar maximum confirmation in late 2024. The SUN is telling us something this summer. The question, as always, is whether everything that needs to act will act quickly enough when the most serious event eventually arrives.